Good morning, everyone, and welcome to Day 4 of ISART. I'm Keith Gremben. I'm going to be the moderator overall for the day. I'm a professor at the University of Colorado Boulder, formerly with ITS, and so ISART's been a big part of my life for a number of years. Certainly hope that everybody has been enjoying the conference so far. I certainly have. Quick note that all the presentations from earlier this week are up on the ISART website. Today is going to be a big day. I think we're going to be wrapping things up with a bang. So as a quick overview, we're going to kick the day off with a technical presentation from Dr. John Shea, one of the members of the Gator Wings team that won the Darpa Spectrum Collaboration Challenge. The challenge was interesting in that it demonstrated the potential of collaborative AI to efficiently and effectively manage and dynamically manage spectrum. Beyond the technical presentation, we have two very interesting panels today. The morning panel is going to cover implementing resiliency in zero trust network operations. And the afternoon panel will be bringing it all together with some new insights and novel connections. I would look to this panel for some real out-of-the-box thinking. So a few notes on logistics before we start. First, please feel free to ask questions online during the presentations and panels. To both the questioners and the panelists, remember to spell out acronyms. Moderators, please remember to look at the questions that are in the QA section on the right side of your screen. Attendees, if you would vote on those, then it'll be ordered and the most popular questions will be asked first. We'll also try to take unanswered questions into the breakout room. And please remember to take advantage of the breakout room. These occur right after the panels, and we are trying to the greatest extent to replicate in a virtual environment these critical one-on-one interactions that happen in the hallway. So there will be breakout rooms after every panel. As a reminder to everybody, after each panel concludes, the speakers and the panelists, the moderators and the panelists will move to the breakout rooms. Please be sure that you exit the events screen, the BlueJeans events, before you enter the breakout room, or there will be crosstalk, which will disrupt the event. For those of you who can download the brand new ISART app, all the information and links you need for the breakout rooms are in the app. For non-app users, the ISART confirmation mail that was sent to you last Friday has quick links that will contain a link and phone number for all the breakout rooms. And for each breakout room, there will be room hosts that will be there to help if needed. If you run into technical difficulties, you can reach out to conference services staff. That's also listed in your confirmation email. Quick technical note that the code to access the main sessions on the BlueJeans events is the same each day. So if you have issues with a link, please just try the next comparable link. And the ISART app will help you with this. By default, the only information anyone will see on the app is your name and affiliation. So if you're interested in chatting with others, networking, exchanging business cards, remember you go into the app and add whatever information you're comfortable sharing. So I'd like to encourage everyone to use those tools to ask questions and converse with the panelists and presenters in the breakout rooms. I've been in a breakout room at every session, and it's been getting better and better and more seamless over the week. So I think you'll enjoy the experience. So with the administrative notes out of the way, I'd like to introduce Dr. John Shea from the University of Florida. John is a professor in the Department of Electrical and Computer Engineering. His research is in the areas of wireless communications and networking with an emphasis on military communications, software-defined radio, networked autonomous systems, and security and privacy in communications. He was co-leader of the team Gator Wings, which was the overall winner of the Darpa Spectrum Collaboration Challenge, which was Darpa's 5th grand challenge, in which the teams used software-defined radios to implement intelligent radio networks for collaborative spectrum sharing. So Professor Shea is going to give us a high-level overview of the Spectrum Collaboration Challenge. So I'll turn this over to our first speaker, Dr. Shea.
All right, Keith, thank you for the introduction. So we can go ahead and I'll try to just give you a very quick some lessons that we learned from the Darpa Spectrum Collaboration Challenge, or SC2, and I'll just try and give you an overview of the challenge as well at the beginning here. So if we could go to the next slide. So as Keith mentioned, the SC2 is Darpa's one of DARPA's grand challenges. It was a 3-year competition to develop and demonstrate the potential for intelligent agents from diverse teams to perform dynamic spectrum sharing. Next slide. Now, unlike systems like Cbrs, in the SC2, teams must optimize spectrum utilization at time scales of seconds and in the presence of diverse users, time-varying traffic flows, and incumbents. DARPA did not require any specific frequency channelization, or it didn't even require that teams use a frequency division approach. So it requires a much greater level of intelligence to achieve that than traditional resource optimization. Next slide. So spectrum decisions are fully distributed. There's no central infrastructure involved, such as the spectrum access system in Cbrs. DARPA also challenged teams with a variety of incumbents, active, passive incumbents, and then different types of interferers that required teams to perform distributed sensing and reporting. Next slide. The main conclusion that we took from the SC2 is that real-time distributed spectrum sharing is feasible today with existing technologies. I think that was well demonstrated if you watched the SC2 championship event. At the same time, we could see there's still a lot of work that can be done to improve the efficiency, ensure privacy and security, and develop schemes that will incentivize good spectrum usage behaviors and enforce violations of spectrum usage policies. Next slide. So a typical spectrum sharing scenario in the SC2 looks something like this. There are up to 5 teams or networks of radios communicating in a frequency band. In the championship event, each of these teams would have 10 radios, so 50 different radios trying to access the same spectrum. In addition, many of the scenarios also contain other non-collaborative radios, such as different types of incumbents and jammers. And then there is a lightweight collaboration protocol called the SIL that allows the teams to exchange some limited amount of information, such as spectrum location and spectrum usage and geolocations. Next slide. So were scored, and yes, right there, that's perfect. And each team's score depended on their success in delivering a vast variety of IP traffic, but the scores also depended on the performance of the other teams in the match through this equation that you see here. And basically what this equation does is create a mixed cooperative and competitive game. There's a threshold for each stage of a match, and if any team falls below the threshold, then every team just gets the minimum score among all the teams. So you want to encourage everybody to get up to the threshold. That's the cooperative part. And then if every team gets up to the threshold, then each team's score is their overall number of points scored. So it's a mixed competitive cooperative game. Next slide. And if you could go ahead and fill this out up through the bottom line, step through it. There you go. So spectrum sharing in the SC2 is based on this very rich set of information, but the information is also very incomplete. In particular, DARPA prohibited teams from disclosing any information about what they were doing in terms of signaling, protocols, strategies, anything like that. There was a complete ban on talking to other teams about that. We don't have any online information about how we or other teams are doing other than estimates that the teams generate about that. And so the teams use the SIL to exchange some information about frequency usage, radio locations, etc., and also some incumbents report usage information. And you can sense the spectrum to determine what is in there and how people are apparently using the spectrum. And so there's a lot of different sources of information, but the information is not necessarily accurate or truthful in some cases. Next slide. So I just want to walk you through a few scenarios real quick. So the first is the Alleys of Austin scenario, one of the simplest scenarios that we had, which is 3 to 5 squads of soldiers are moving through Austin, Texas. They are sharing 20 megahertz of spectrum, and there are 3 stages, and as the stages progress, the amount of traffic that is being given to the teams to deliver is increasing. And the teams have different amounts of overlap in terms of their spatial reuse because they are sort of moving through this urban environment. In stage 1, you just have some voice over IP flows and command and control streams. By stage 3, you have all of that plus many file bursts that come in that are quite large, as well as many video streams. Next slide. And just to show you an idea of what sort of information we would get out of our own tools at the end of a match. So on the left, we have a graph that shows the score per measurement period across each of the across time, and the 3 stages are marked. These are 3 of the best teams in the championship event. And so the scores evolve as more and more traffic is added into the different stages. On the right-hand side, we see a snapshot of the spectrogram in stage 1 and stage 3. As you can see in stage 1, the traffic load is relatively low across the teams. Teams can find a distributed allocation that's completely disjoint, and everybody can handle their traffic. By stage 3, everybody is transmitting on other teams' channels, and you hope to find the channels that allow some spectral reuse, spatial reuse. Next slide. Slice of life scenario. Each team sort of represents an internet hotspot with a pool of users around it in a congested urban environment. And the teams have different levels of traffic at different stages. So in each stage, there's one team that sort of has surge traffic. And so those teams need to use more spectrum to score more points. However, the other teams have some incentive not to let them necessarily score as many points during those times. And again, when you have this surge, you want to find those places where you can do spatial reuse. And so you can see if you look at a little pie chart here on the screen, it shows a percentage of spatial reuse. So at this time, there was 200% of the total. So everybody's overlapping with somebody pretty much. Next slide. So in the passive incumbent protection scenario, the teams must control the total amount of power, interference power that's being received at a passive incumbent, such as a radio astronomy antenna. The incumbent is not transmitting on the band, but he's listening to something, say, from outer space. And he will report to the teams his amount of interference received and his tolerance, which is a ever decreasing threshold for interference power as the stages go on. And if the teams as an aggregate ever exceed the amount of power that he allows, then the team scores 0 points. And that's what you see in the graph on the very lower right corner. In the third stage, the teams as an aggregate transmit too much power and there's no points scored. Some teams don't realize they have to turn off everything for a while because the threshold drops so low, and so it gets violated. Next slide, please. So in the active incumbent scenario, you have an active incumbent. Here it's like a vehicular radar that is sweeping around, and you have to detect it in the RF spectrum. It's probably hard to see on your screen, but if you check the slides, you can kind of see it in the detail. And again, all the teams have to avoid transmitting on that channel during the times that the radar signal is present. Next slide. And then finally, here's the jammer scenario. That again, the spectrograms are at the top, showing the jammer on. Here it's a constant jammer. The jammer had different behaviors: constant, sweeping, hopping. On the right, the jammer's off. And then there were many stages with the jammer going through different types of behavior. The next slide. So our strategy for the SC2 was basically to build everything as flexible, agile, and robust as possible. We wanted to be able to try to find those opportunities in time, frequency, and space to fit in with the other teams. So we designed our granularity to be quite small to achieve that. And we tried to have a very robust physical layer to tolerate interference in terms of our coding, modulation, adaptive, everything's adaptive. And then definitely adapting as many different things from the physical layer, link layer, network layer, and then we also even have the ability to do jamming to other teams. So there were many different knobs we had to turn to control our radio system, and so that was one of the things we tried to achieve. Next slide, please. And if you could step ahead. Down through, this. So our spectrum sharing decision engine basically tries to maximize our team's match score, and that is based on determining which flows we're going to transmit, because sometimes DARPA gives us hundreds of flows. We can't accommodate them all. Depends on the interference environment, lots of different things. Which channels are used, we should use, and which radios should use it, which flows we send in which little time frequency resource units, which we called pockets. And action space, you can see, is huge. We had a recurring time slot schedule that was 10 time slots per epoch, so we had 400 pockets if we used 40 channels, which was our maximum. We had over 100 flows sometimes, so you can see the number of possible pocket schedules we could create was an immense number. Next slide. And the state space was also huge. The inputs to our decision engine included our team's quality of service information, all of the different flows we had to support and how we were doing in supporting them, how many points they were worth, the channel information, link quality, which we got from our spectrum sensor, information from the other teams, which we used to build a interference map, and what was our achieved throughput per pocket, our peer information, who they were, we tried to identify them, and how they were doing for each of their flows. And this also produces a huge amount of information. Next slide. Perfect. One of the first things we realized is that the decision engine couldn't be solved by just some black box solution. Just the state space and action space are just too large to ever train. So we applied the typical engineering approach of decomposing the problem into smaller pieces. Our pieces were basically channel selection. Which channels are we going to use? Admission control. Which flows are we going to support? And then pocket schedule assignment. How are we going to put those individual flows into an achievable schedule based on our constraints on the number of simultaneous transmit and receive streams at each radio? Next slide, please. And so we did develop a couple different approaches to doing some of these things. So in terms of channel selection, we had basically a heuristic approach designed by me. We had a machine learning approach that one of our PhD students worked on. And one of the sets of dots is missing here, so I can't show you the performance, so I won't say too much about this. But basically, we found that the ML system was pretty competitive with the expert system, but not quite as good in general. And we just couldn't count on, the expert system overall had the better performance, and we were more confident in it because we understood what it was doing as it went into different new scenarios. So next slide, please. So basically, the SC2 demonstrated that distributed spectrum sharing among a very heterogeneous set of intelligent agents can be achieved with spectrum access occurring in time scales of seconds instead of hours. The teams demonstrated an acceptable level of performance in the presence of all these diverse challenges I mentioned, so mobility, traffic surges, incumbents, jammers. And one of the important things that we definitely observed and we heard a lot of feedback about is that we spent a lot of time optimizing our particular behavior to the rules of the championship event in the end. And that made our agents much more competitive than cooperative based on the scoring rules that were announced. So it's always important that reward structure will drive the spectrum sharing behaviors. Next slide, please. And go ahead, there we go. There were a lot of problems that limit the ability of teams to apply machine learning for this championship, this competition. So I don't think many teams even tried it. We tried some parts of our system. As I mentioned, the overall state and action spaces are really huge compared to many problems. And that's especially true in comparison to the amount of training data that you can collect. And I'll say a little bit more about that later. But we also found as we went to the last few weeks of the leading up to the championship when we had to submit our radio algorithms to DARPA that teams were changing things very rapidly, their strategies, but also their radio algorithms even, the fundamental radio algorithms. And the ML training just couldn't keep up with that. So we felt much more confident in the expert system approach based on that. Next slide, please. So Applying dynamic spectrum sharing techniques like those in the SC2 to real systems will require the development of what we call a technical ecosystem for DSS. In particular, some of the important aspects of the SC2 that may need to be considered are the design of the incentive frameworks to drive the desired behaviors, and the development of an information sharing protocol. One of the nice things in the SC2 was the development of this SIL, which allowed us to exchange some information with other teams. And there's a lot of work still to do on how to make these algorithms more efficient, how to preserve privacy, how to achieve security, how to have compliance and enforce that. So there's many things still to be done here. Next slide, please. So I think a lot of people are interested in how ML and AI can be applied to this, and we do see a lot of potential for those in dynamic spectrum sharing, but new approaches to training agents for that will need to be developed, and ML agents will need to be developed that we can be confident are robust to new situations, because always we can't provide the training algorithms with every possible situation it may need to operate in. And we also see a lot of potential for machine learning approaches to compliance, to privacy, and also to adapt the overall incentive structure over time to enhance the network performance. Next slide. So I'd be remiss if I didn't acknowledge all of my teammates, especially Tan Wong, who was our team leader, who did most of our physical layer, our MAC, and the sensing and spectrum mapping portion of our radio. David Green, who did our FPGA, some network layer, a lot of IDE and tools. Tyler Ward, another PhD student who did some physical layer work on acquisition, link layer, and most of our control plane. Marco Menendez, an undergraduate who did a lot of work on our workflow and some SIL development work. Next slide. And then Caleb Bowyer, who did machine learning, Ximing Deng, who did visualization, Quanfam, who did channel emulation tool we were developing, and Josh Agarth also worked on SIL, and especially Darpa, the SC2 team, for running the competition and developing the Coliseum, which we're still using now, and the Darpa SC2 prize and an NSF grant that helps support our team's efforts. So thank you for having me here. I see there's some questions, so I guess I'll just answer the questions if that's okay.
Right ahead. Thank you.
All right. So the first question was hidden terminal problem and issue in interference management. Well, hidden terminal is a little bit hard to exactly specify in this, but yes, absolutely. So we would collect information from all of the other teams about where they would say their radios were. Not all teams were good about reporting that. If we knew that, then we could kind of prevent hidden terminal because we knew where their interference would be causing interference to our receivers. But if they weren't reporting it, then yes, we would be transmitting based on what we could sense from one location, but we didn't fuse all of the sensing information from all the locations into one place because just the overhead of exchanging that much information. And another question was, is jamming avoided by switching to a band channel time which is not jammed? And yes, we could. There was always unjammed space, but that's not necessarily what you wanted to do for all of your flows because those were the areas that all the teams wanted to use. So we preferred not to use that all the time. We sometimes would put our easier to transmit flows within the jammed region because we could still get them through with a robust physical layer and put some more, say, high data rate flows outside of the jammed region.
Okay, thank you, John. We're out of time here and need to move on to the panel, but thank you very much for a great presentation.
All right, thank you.
And people who had questions for John, remember he will be in a breakout room at the end of the panels. So now let me shift over to our first panel. Our next panel is a great collection of experts from different industries and different backgrounds. And it's going to dive into the complex issues of operating with resiliency. So our panel moderator is Dr. Paul Zablocki. I first met Paul when he was the director of the Army Communications Electronics Research Development and Engineering Center. That's a mouthful, so we all call it CERDEC. And he was the director of the Intelligence and Information Warfare Directorate. He moved from there to the Office of Naval Research and is now a program manager in the Strategic Technologies Office of the Defense Advanced Research Projects Agency, or DARPA. At DARPA, his programs focus on enabling joint operations and robust communications, among other areas. So now I'll turn this over to our moderator for the first panel of the day, Dr. Zablocki, who will introduce the other panelists.
Thanks, Keith. I appreciate that. So good morning and welcome to panel 4. My name, as Keith said, is Paul Zablocki. I'm a DARPA program manager in the Strategic Technologies Office. My research interests range from robust communications and tactical environments to electronic warfare, and I've worked in all of those areas. On behalf of the panel 4 members and myself, I'd like to thank the National Institute of Standards and Technology, the National Telecommunications and Information Administration, and the University of Colorado for hosting this event under such challenging circumstances. Panel 4, as Keith mentioned, examines both implementing and maintaining resiliency in zero trust networks. So I've worked in this area of electronic warfare for a long time, but decided I really ought to look up what resiliency means. And so according to Wikipedia, resiliency is the ability to provide and maintain an acceptable level of service in the face of faults and challenges to normal operations that range from simple misconfigurations to large-scale natural disasters and targeted attacks like I would cause. We've assembled a panel of 4 experts from a diverse set of industries and academia to help explain how they address network resiliency in their respective areas. You'll find full bios on each of the panelists on the ISART 2020 website, but I will provide brief introductions to each of them. So I'll go through the bios of the 4 participants or panel members. We have Tim Godfrey. He's a technical executive from the Electric Power Research Institute, and he'll address some of the challenges that utilities face as they enhance their telecommunications infrastructure to enable grid modernization. Next, we have Milo Midden. He's Vice President of Wireless Services at Google and will help us understand resiliency challenges from an internet-related services and product perspective. We have Dr. Wayne Fowle, and he's currently a visiting research engineer at the University of Maryland Institute for Systems Research and the owner of a small Eponymous research and development company. Now, you'll find that in his bio, and I actually had to look up what Eponymous means, and it is, in fact, a company named after himself. He'll provide us insight into some of the unique defense-related challenges that we face. Our final panelist is Dr. Sengoyita Sundri, and Sengoyita is going to talk to, she's Vice President of Technology Development and 5G Labs at Verizon's, and she'll help us understand zero trust network resiliency from a major service provider perspective. And so with that, I'm going to turn it over to Tim for our first discussion of the day, and we'll go through the 4 panelists' overviews of the topic, and then we'll hit questions afterwards. So Tim, take it away.
Thank you, Paul. Good morning, everyone. Next slide, please. I'm going to give a brief overview of 4 projects and research areas that we have that are related to resiliency and network operation, and also have to do with spectrum. Next slide, please. EPRI is a collaborative research organization, a nonprofit that works with multiple utilities dealing with common problems that are faced globally. Next slide, please. One of the big areas that is driving our work in telecommunications is we call the transition to the integrated grid, which is based on the need to modernize the grid to support renewables and widespread adoption of distributed energy resources, which have significant impacts on the power flow and the operation and management of the grid. Next slide, please. One way that the need for this telecommunication in the field is playing out in the industry globally is the adoption of LTE and the movement toward 5G. And in particular, there's a strong momentum toward the adoption of private LTE, which is not entirely exclusive of commercial, but is being used as the core network for operational purposes. That is due to reliability, availability concerns with commercial networks. The utility is able to build and operate the network to their own standards. Cybersecurity is a big issue, to be able to control all aspects of the network security and also have full visibility into the operation of the network through your own NOC. Cost is another interesting factor. When you first think about it, you think that building your own private network would be prohibitively expensive, but for utilities, especially investor-owned utilities, capital expenditures are preferred over ongoing operational expenses due to the way that they handle their finances. Finally, a big issue for many utilities is the life cycle. Commercial networks are often out of sync with the expected field asset lifetime, and they've been forced to retire equipment in the field early because the generation that they were built to was no longer being supported by the commercial networks, but the assets were still fully functional. Next slide, please. Of course, the cost of the spectrum is a large issue, and that's something that we think a lot about, is how to get spectrum or how to make different spectrum choices, including shared spectrum, work for a private LTE network. The cost of the required infrastructure for full coverage is also challenging. The networks for private utility tend to be more coverage limited rather than capacity limited, which is the problem for commercial networks. And finally, operating, building, and deploying a network is a new skill set for many utilities. Where does 5G fit in? It's certainly an inevitable endpoint, as the whole industry will be moving toward 5G over time. It doesn't immediately solve the spectrum issues for private networks. In fact, it makes it a little more complicated. Currently, the new radio is limited to 5x5 as the smallest channel size. Most of the utility networks that are operating in the United States are using 3x3, so that's a little bit of a challenge. New radio light is moving in the right direction toward giving a little more flexibility. Another bit of good news for the migration to 5G is the advent of dynamic spectrum sharing, which allows same spectrum allocation to transitionally move from LTE to 5G, incorporating both. Next slide. One other area that we're starting to investigate is how to find the appropriate spectrum. I've mapped out the spectrum options on two axes. From left to right is the frequency band, which is very important because the coverage is desirable. From the bottom to the top, it's a what I call the difference between prime or non-prime spectrum, where at the top, the commercial spectrum that's widely used by operators is available in some areas, less populated areas, but it tends to be expensive. Bottom, see the narrow, encumbered, or shared spectrum that are less attractive to commercial, although some commercial adoption is taking place, especially in the Cbrs. Next slide, please. Within those bands, we can look more closely at those that are shared. These three areas demonstrate the three ways that the spectrum can be shared. In the unlicensed bands, it's shared very granular basis, almost packet by packet. CBRS is controlled by something like SAS, which is controlled maybe on a day ahead or shorter based on some circumstances. And then we're starting to look at the opportunity to share federal spectrum in the 406 megahertz band, which has the potential for harmonization with band 87 and 88 in Europe, which would be on more of a long-term sharing basis with incumbents. That's something that we're investigating with the DOE and Idaho National Labs. Next slide, please. Finally, we're starting up a new project on LTE and 5G security, which is more about the underlying standards and validating, replicating, and mitigating some of the exploits and issues that have been published in the research community. We're just getting started on this and hope to have it underway next year. Next slide, please. Another area that's just come up this year has been the changes to the use of the 6 gigahertz band. This spectrum has been exclusively used for licensed operation over many years. This year, the FCC opened it up to unlicensed devices. Next slide. The net effect is that the band has become effectively shared, and our testing that we've conducted has demonstrated that the automatic frequency coordination system is going to be responsible for preventing interference with these fixed services, and there will need to be careful attention given to the existing equipment, including side lobes. Next slide, please. Finally, we have a black sky communications project that we did last year that looks at communications in the case of restoration for a widespread outage. Next slide. This project investigated non-terrestrial systems, including satellite and HF radio over a wide area. I don't know if the slides you're keeping up, they're stuck on my screen, but I'm now speaking to the final slide on the resilient communications, microgrid communication, which is the fourth area that we're looking at, which is taking advantage of peer-to-peer communications on LTE, such as ProSay and PC5 Sidelink, to allow communications supporting a microgrid, which provides power locally in case of a broader outage, to be able to also transition to a localized autonomous area. So hopefully these ideas will stimulate your questions and thoughts, and we can have more of a discussion in the breakout room or questions. That's all. Thank you.
Hey, thanks very much, Tim. I think next we're on to Milo Midian, and if you're ready to go, take it away, Milo. Are you there, Milo? All right, we appear to have lost Milo. Maybe we will move on to...
Can you hear me now?
Oh, yep, can hear you now. Great. Excellent.
For some reason, the app keeps switching audio devices on me. First off, thank you for inviting me. And since I serve on the Defense Innovation Board, I wanted to say that up front, these are my personal comments and do not necessarily represent the views of the Defense Board, its chair, or the Department of Defense. I just have to give that boilerplate away. Google was one of the first firms to adopt a zero trust architecture for our internal systems. This was the result of looking at how PLA hackers penetrated our systems back in 2009. And those lessons learned drove a change in our architecture that resulted in a system called BeyondCorp, which is sort of our implementation of the zero trust internal network. Key to this model was not ascribing any rights to access information by being on a particular network segment. We assume the entire internal network is open and unprotected. That isn't actually true, of course. We use 802.1x authentication on switch ports and enterprise Wi-Fi and network segmentation. But the key is to not use any protocols or access control methods that grant rights or to devices by what network segment they reside on. That means we rely on internet protocols that require cryptographic authentication for access to information. These are the protocols used for internet services, not things like NetBIOS or Windows file sharing. Devices that want to access a given network resource must be certified and have been loaded with cryptographic certificates that validate it's a device that is authorized. That could be a desktop computer, a laptop, phone, tablet. Users that want to access information must use multi-factor authentication to validate their identity, and then access is granted to information based on the roles and the identity of the user and device. For example, someone in our finance org would not have access to source code that a software engineer would, and a data center hardware engineer would not have access to a personnel database. When people change roles, their access rights change without explicit updates being made to code repositories, etc. That's not to say that network location is invaluable. We treat it as a signal, not a key. For example, if my laptop shows up on a network segment in our DC office, but my ID badge was just read accessing a door in my building in Mountain View, that will trigger a security alert and could remove my access to information until that discrepancy is resolved. Patterns of data flows are used to train machine learning models to flag unusual activity and help automate threat detection and defense. Because of this model, it allows us to be flexible about what network resources are used, and we can use a mixture of private and public network access. Zero Trust was critical to enable us to move more than 150,000 people to work from home mode in about 2 weeks. Because we didn't trust the network in our offices, we could actually move the same equipment to operate from people's homes on public networks without wholesale changes to software and systems. When you use G Suite and other Google products, you're using the same technology that we ourselves use to protect information across untrusted networks. When I think about how this could apply to DoD and federal missions, there's several implications. One of the major issues I see in the military that holds back innovation and integration of new types of networks, particularly wireless ones, is this mistaken focus on communication security and not information security. Putting a pair of KGs on a point-to-point circuit may protect information flowing over that link from interception, but it does nothing to protect that information from an insider attack at the local networks on each side of the KG. It also means that newer, faster, and more compact encryptors have to be built to deal with each different type of network needing to be integrated. That's a real issue, especially when it comes to highly integrated devices like mobile handsets. Instead, if the Zero Trust model is used, much lighter weight encryption can be used on the communication links, and the data is protected as it flows over the complete network path. This allows the use of commercial networks, as well as streamlining integration of new technologies and dynamic reconfiguration of networks that will be critical in wartime. It also allows the mixing of flows of data with different security levels and different access rights on common network infrastructure, depending on the encryption for segmentation and protection, not hard separation of flows that are increasingly devoid of meaning on higher performance wireless and optical network infrastructure. That end-to-end encryption, where not just the server is authenticated to the client, but the client is authenticated to the server, and that identity and role are used to grant access on a fine-grained basis, is the key to modern security that scales, and scales to literally billions of users, and to securely accessing resources on cloud infrastructure. Just as DoD decided long ago not to build its separate computers, operating systems, and programming language, but follow the commercial sector in IT systems, it means we'll also need to adopt a zero trust architecture, because that's where the commercial sector is going, particularly in a COVID-infected cloud-native world. One thing I want to flag here, this notion of relying on end-to-end encryption and management of identity at the endpoints has fundamental problems for organizational models where some firewall is meant to inspect traffic in the middle of that encrypted communications. IT models where security teams insert themselves between clients and services are very much challenged by this model, because to do so, it means creating holes in the encryption security to do man-in-the-middle attacks on those data flows, instead of managing device and application security at both ends. That used to be the model, but industry is rapidly moving away from that because it's not the way the internet and cloud-native systems function anymore. One other point that is that we believe encryption needs to be adapted and upgraded rapidly, not just to deal with vulnerabilities that are discovered in algorithms, but also new kinds of attacks from quantum and other kinds of specialized computing systems. After the Snowden disclosures in 2013, Google moved to a zero trust model in our core data center networks in the span of only a few months. Today, our systems do not trust the very data center switching fabric that interconnects our processors inside a rack. Not only is traffic between data centers encrypted, but traffic between compute nodes in the same rack is encrypted as well. That kind of adaptation is not possible with hardware link encryption being retrofitted in a wide area network, but will be needed to stay secure in the face of new kinds of attacks. As DoD and the US government move to more commercial models for computing and networking, policies and maybe even organizational models are going to have to adapt if they don't want to be left behind in a slower and less secure infrastructure. As my pilot friends in the Air Force say, speed is life. That's true in IT as well. Being static and adapting and not adapting quickly doesn't make you more secure. It makes you a target. Thank you.
Thanks, Milo. That was great. Wayne, I think you're up next.
All right, great. Thanks, Paul. Sorry for throwing that SAT word at you in the bio, but if nobody learns anything from my talk today, at least hopefully they've learned what eponymous means. I want to thank also the ISART organizers. I tuned into a bunch of the panels earlier this week, and it actually caused me to rethink what I wanted to talk about and how I wanted to talk about things today. So thanks, guys, for putting together a really interesting and diverse set of speakers and the thought-provoking program today. I wanted to, touch a little bit more on my background. So currently, I'm a visiting researcher at the University of Maryland. Prior to that, most of my work was defense R&D at MIT Lincoln Laboratory and a few years at Darpa as a program manager as well. So I'm kind of spanning that base of seeing what's going on in academia, but with a background from what defense needs are. I also want to acknowledge a new university-affiliated research center at the University of Maryland called the Applied Research Laboratory for Intelligence and Security, or ARLIS. A large amount of the work on 5G and communications networks that's done at the University of Maryland comes through ARLIS. So I just wanted to acknowledge them. So if you go to the next slide, what I thought I would do, so my title slide talks about zero trust, resilience in 5G. So I wanted to talk a little bit about how I think about that. And when we talk about zero trust, what do we mean? And to whom does that matter? Milo did a great job of describing what zero trust is, so I'm not going to go into that. But when I think about how we're thinking about applying in a bunch of different ways, I believe there's two views that we can think of it. One is how I think it's been talked about most over the course of this conference, which is from if I'm a network operator and putting together a network and operating that, what is it that I should trust or shouldn't I trust? So there's the components that go into my network, the employees that are configuring and managing that network, as well as the users that I allow onto the network. And these are all the entities that I have to worry about who could potentially do something, or what could do something wrong to my network operations. If I'm a user, if I'm someone like the US government who is working over somebody else's network, or the Defense Department, or as Tim reminded me earlier today, if I'm a utility, I also can't trust or don't know whether I can trust all those components, but I also don't know necessarily potentially how much I should be able to trust the network operators that are running that network. So it's, I think, just a different perspective for people to think about. If we go to slide 3, I want to talk about a little bit about access control and the different functions that go in. Milo talked a lot about these things in the lower left-hand corner that are some of the topics you would hear about with zero trust. Making sure that you really know who somebody is, really breaking down the pieces of your network into smaller chunks so you can contain any kind of bad activity. And then this really important role-based access, which also gives, as he pointed out, much more dynamic control. As my role changes, it's a lot easier to change my access. But I also don't think about this concept of trust as being really a binary thing. Either you're trusted or you're not trusted. But I think you can think of it as having much finer grained scale of trustability. And in order to do that, I think we can think about behavioral monitoring. So the first program that I started at DARPA was called Wireless Network Defense. And it was really focused on ad hoc networks, but it was looking at attacks against the control plane of those ad hoc networks, where there are, these nodes are already approved parts of the network, but they could be doing bad things to the network, whether it be intentional or unintentional. We want to be able to understand from how a node behaved, even though it's checked the boxes as to whether it's supposed to be there. Should I be allowing it to be part of my control system? So we broke down, one of the approaches we took was to break down the protocols into basic components, and then also assign nodes soft metric of how much we trusted those based on how we saw them behaving over time in the network. And I think there's what's developed in the 5G architecture has some similarities to that model we were looking at. So there may be some things we could learn from this trust network overlay that we looked at in this wireless network defense program. Then we go to the last slide, talk about resilience. And in that Darpa program, I had two terms I talked about. One was robustness, and the other was resilience. And I defined robustness as really the ability to take a hit and keep operating. And the resilience was the ability, once I've taken that hit, to reconstitute my network and get back close to my original performance. And in order to do that second part, you need to understand when you've been hit, where it's happened, and characterize what that attack or the event was. And for that, you need some internal awareness of what's going on in your network. So I think we could use this concept of multi-level trust metric to aid in that adaptive control of our networks. And I'm really intrigued as we look at what's coming in 5G and the ability to customize virtual network functions. I'm really curious to know if there's some way to take those and enable those to help with monitoring, evaluating trust, and then reconstituting the network. So there's my thoughts. I hope they spur some thoughts in you guys, and I'll look forward to the rest of the conversation in the panel. Thank you very much.
Hey, thanks, Wayne. That was terrific. Senyogita, I think you're up next.
Thanks, Paul. Can you hear me? Okay. First of all, thank you for inviting me. I'm honored to be here with the panel, and happy to talk about what 5G and zero trust architecture mean to a service provider like Verizon. So first and foremost, I've been with Verizon for a few years now. Spent a lot of time on the network side, and I'm more focused now. Led some of the early 5G work in terms of mobilizing the industry and working with the industry, as well as the FCC and CSMAC and others in terms of bringing spectrum to the industry. So this topic is near and dear to me, and I'm happy to talk about some of the other aspects of 5G in terms of security and what the flexibility of 5G provides, and the opportunities, as well as look at where there can be differentiation. So the introduction of 5G into the communication ecosystem is probably the first tangible example of the fourth industrial revolution, right? We've had several new features of 5G that enable many more things than they were previously possible, essentially bringing the cloud into the hands of the device. So the capabilities of the cloud in the device. What that means that our generation will have access to more data and more machine intelligence than ever before, and be able to process that in near real time so that we can make decisions. Understanding 5G's capabilities is the first step in leveraging the full capabilities of this wave. We also know that the 5G architecture and standards bring a lot of flexibility in design and deployment of the network in terms of virtualization and service-based architecture, which allows us to be agile. And like my previous panelists have talked about it quite a bit in terms of, if you're not fast enough, you are going to be left behind. So I think those are some good things. However, the design and deployment of the network, the 5G network, are important and play a big role in how you offer continued security. And so I believe that not all 5G networks are equal in that sense. And that's also especially important because 3GPP as a standard offers a lot of optional capabilities that not everybody may choose to deploy, and that might impact how secure the network may be. So Verizon has structured our approach for securing our 5G network around 4 pillars, right? So one is the global security capabilities. The first pillar of our approach is securing our 5G network, is leveraging the existing global security capabilities that we have in place that also support all our communications today, which is 4G as well as wired networks and so on. So first one is enterprise protection, such as physical security of our facilities, penetration testing of key systems, and enterprise vulnerability management program. Sometimes it can be a lot of process, but it also ensures that we are able to manage and secure our networks. We have global security operations centers, supply chain security practices, and security governance programs, and so on and so forth. We have partnerships in place to continuously exchange ideas with industry groups. I don't have to talk about that in a lot of detail. And as well, a global backbone network that provides visibility into worldwide threat actor behavior that Verizon uses to inform the defense of its network. The second pillar is the features in the 5G standard. Like I said before, there are a lot of new security features that are part of 3GPP's 5G standards. Verizon, we will implement numerous optional features to enhance security, and that has influenced our implementation decisions. For example, device security features that include protecting information that could be used to identify and track a subscriber, prevent attacks from modifying user traffic, as well as ensuring subscribers only to connect to trusted sites. Radio access network security features, which provide secure communications on all RAN interfaces. RAN is the radio access network, as well as include extra protections at place that are vulnerable to physical attacks. The third is the core network security features, which include specialized network functions and enhanced protection for service-based architecture that the network functions will use to communicate. The third pillar is our own unique capabilities, our design decisions, building upon the robust 4G LTE security principles, as well as tailoring redundancy models and security protection for each network function-based functionality. Implementation of robust device certification processes. Again, it may seem cumbersome, but it really helps us ensure that we are hardening every network interface and every device to network interface, securely provisioning and booting network functions, and so on. The third is the deployment capabilities involving core services such as PKI, access management, analytics, and vulnerabilities scanning. Finally, the fourth pillar is enabling customer-facing services. So we embrace the concept of zero trust architecture early, and we provide solutions such as software-defined perimeter today that's unique to the network, and it will continue to offer that in addition to the security notions that 5G provides and the capabilities that 5G provides, such as network slicing and edge computing. You can think about those as limiting the levels of isolation. Slicing, especially, you can think about it as providing a level of isolation and resources guarantees to a certain part of the customer, so you can separate different types of users into different slices. Edge computing, not only will it host latency-sensitive applications, but you can also host network-based security services, maybe even SDP in that framework to continue to strengthen the endpoints that may not be secure. So 5G can seamlessly support an application in addition. So having said that, we can seamlessly support any other application that uses zero trust architecture to communicate end to end. And of course, not to forget, as we look at new capabilities that technology that evolves, we continue to look for ways we can continue to strengthen the network, such as providing using the capabilities of quantum key encryption and so on, to continue to strengthen the network as these technologies evolve and make these provide added security to the network. Next slide, please. So some of the key examples of 5G security that we have implemented, I've given you a high level before. I'll go into a little bit more detail here. So devices on Verizon's network will automatically use an encrypted identifier called subscription concealed identifier when identifying themselves to the network. So this identifier is generated using cryptographically strong encryption keys that come pre-configured in a tamper-resistant hardware element on the device. And it also encrypts metadata that could otherwise be used to track the user and compromise their privacy. Secondly, 5G networks break down large multipurpose network functions from 4G LTE into smaller single-purpose network functions that are deployed in a distributed manner. So this is the new architecture that we was talking about. So Verizon's 5G will leverage this disaggregation to deploy network function in a way that eliminates single points of failure. So you can think about it as offering the flexibility that we've taken this flexibility and to ensure that we have eliminate the single points of failure and minimize the blast radius of a network function failure security issue. In other words, a malfunctioning network function will impact a smaller number of customers than a similar failure would in a 4G LTE network. The distributed 5G RAN, right, again, will have network functions at the edge of the network, potentially at unmanned locations or sites with minimal physical security. Our network will ensure that these distributed network functions cannot access cryptographic keys, protecting subscriber traffic, thereby protecting the network from an attacker physically compromising the site. And the next is the service-based architecture in the core will cryptographically authenticate the identities of any network functions trying to communicate with each other. So while there are several more interfaces available today, they are going to be cryptographically connected to ensure that you can get access to these interfaces that easily. So encrypt all network function communications as well as cryptographically authorized communications between network functions using modern security standards. The 5G devices go through a rigorous certification process. I mentioned that before, and including penetration testing by a specialized team that has deep understanding of how the network works. So we have several in-house security personnel in place. And any application service that we test and launch has to go through that security posture testing and threat modeling and risk modeling and so on. The 5G network functions that I mentioned earlier and the containerized network functions that they'll run on the cloud platform. So this is a little bit of a departure from the 4G network that we said, right? It offers that flexibility. But these functions don't just run on any cloud, they run on Verizon internal cloud. And we are hardening the Verizon internal cloud to ensure that we have all the monitoring tools, physical security and so on, with firewalling and so on and so forth. And they also leverage common PKI for identity and many other features that ensure security of the Verizon internal cloud. So since 5G is an evolution of 4G LTE, these four pillars and their associated features build upon 5G security, but also improve upon it in a key areas with the flexibility that 5G offers. And the 5G implementation that we have goes further by the additional capabilities that we have in place already, right? Combine these things, we make sure that we are more secure and ultimately enable the fourth industrial revolution. So if you want more information on some of these concepts, you can download the white paper that I've provided a link to, as well as our annual mobile security index that does a whole lot of testing on various networks today and provides data on how things are, what are some root causes of security breaches. That's all I have. Thank you.
So thanks, Sanyogita. That was terrific. So we have plenty of time for questions, and we're actually getting some questions. And so I'm going to jump in and take a look at some of the questions and read them out to the panel. First question we have, which I think I'm going to generalize, but we'll start with Milo answering it. Was there any trade-off with overhead based on Google's zero trust? And Milo, if you can take that, and then I'd like to ask the other panel members too to take a shot at that from their perspective.
Sure. So I'll answer that in two ways. Originally, when we turned it on our data center network, right? I think it was something on the order of 10 to 15% of CPU overhead to do that level of encryption across everything, right? Not trusting the data center fabric, et cetera. That changed as new CPUs had more and more cryptographic support in their instruction sets. And so that's been optimized significantly. And so I think it's probably under 5% now, but obviously varies on particular platform and function. I would say also, if you think about zero trust from an encryption perspective on sort of user traffic going end to end, right? SSL and the rest had a fair amount of overhead. QUIC and HTTP3 are actually reducing that kind of overhead for significantly. And so I think that you're going to find that, particularly on slower networks, that the amount of overhead to do zero trust is actually quite modest.
Thanks, Milo. Tim, I would think that overhead's a big issue for utilities. Have you done analysis on the overhead implications of zero trust?
We have not. Yeah, definitely, it's true that overhead is a big issue. I saw the question on the 3x3 and 5x5, and as I was pointing out, that many of the private utility networks are based on relatively small spectrum allocations, which means there is a limit on throughput. So today, most utilities are implementing traditional IPsec tunnels and other types of encryption. But this whole area of zero trust is something we are interested in evaluating and getting it adopted. So I think Milo's absolutely right. There's opportunities for zero trust to reduce overhead and make more efficient use of the limited bandwidth that we have on these networks.
Thanks, Tim. Sanjogita, I'm sure overhead's a critical issue for Verizon's, and we'd like to get your thoughts on that.
Yeah, I think, I mean, to add to what somebody said before, I think Milo said, I think the cloud architecture in the beginnings, did receive some initial criticism, but as you can see, it's probably the most robust in terms of security features. And really, a lot of the risk comes from connecting to the cloud from unsecure networks. So to talk about, I mean, there are more details in that, but for example, devices today connect from unsecured Wi-Fi 3 to 4 times a day, and typically those are networks that you connect from, like in a restaurant or a retail store and so on and so forth. So of course, I'm going to talk about. I mean, I guess I'm thinking about the overhead in a way that it is. It can be even if the overhead is there, even if it is large. I think you have to kind of work with that, because you can't talk about you can't I guess minimize the importance of security for the customer. So that's why we believe that nothing, no network is especially from a customer viewpoint, the software defined perimeter is an important aspect of security, and we offer that to all networks today.
Thank you, Sanjogita. Wayne, any thoughts on?
Yeah, I wanted to. I think echo what Sanjogita just pointed out. Right, is that we shouldn't be thinking about it as the communication service and then security as being separate to it. Right, it's all part of one big optimization function, and so you need to. It's harder to do, but you got to figure out how to balance that overhead with what the consequences are of something bad happening if you're not implementing some sort of system like this. And so I think that's one of the other ways you just need to really think about it. It's just, what is the right metric that you're using to judge network performance, and it's not just throughput.
Thanks, Wayne. So we'll move on to the next question. And Tim, you kind of alluded to it, but can you please elaborate more on 5x5 versus 3x3 issue?
Sure. Thanks. The issue is that, as I was trying to point out, that most utilities that are implementing private LTE networks will have to use smaller spectrum allocations. And most of those that are being currently deployed or are being considered are built on 3x3 spectrum. And that is, of course, much smaller than commercial networks that are using 10x10, 20x20, or even much larger than that with 5G and frequency range 2. So 5x5 issue is that with the current specifications for the new radio, the minimum channel size is 5x5. So those utilities that were operating in their 3x3 allocation, they don't really have room to grow. So without having to go back and find more spectrum, which would be economically unfeasible, there's a limited path for adoption to 5G immediately. But the good news is that the NRR Lite will bring back those smaller allocations for the applications that are less bandwidth intensive, because new radio is really, this first rollout was for enhanced mobile broadband, which is high bandwidth. So I'm sure the thinking was nobody would be really seriously operating EMBB in 1.4 or 3 megahertz of spectrum. Make sense? Hope that answers the question.
Thanks, Ken. So we have a few more questions. And this will be another one for the entire group. To implement zero trust in 5G network, what changes in 3GPP specifications are needed, i.e. certification, management, revocation, G-Node B authentication, etc. And maybe I'll ask Wayne to start that one out.
Something's wrong with my mic here, Paul. I was hoping you weren't going to call on me first. I say I'm not super versant with detailed 3GPP specifications, but I think certainly adding some of the one of the big things would be adding something about that role-based access control would be something that you would need to change. I suspect a lot of the other features you need are probably in there. It's just a matter of how you actually configure things. But I'm going to defer to the people who know a lot more about detailed 5G specs for some of those other answers.
Thanks, Wayne. Sanugita?
I don't know that changes are needed. I think there is a lot of flexibility, and 5G does support a cloud-based architecture. And like I said, there are several optional features that are available. So I'm not 100% sure that maybe changes needed. I think I'll have to get back on that.
Thank you. Milo, any thoughts, comments?
Sure, absolutely. First off, no changes at all are going to be required. And the reason for that is that the whole point of zero trust networks is not to trust a network. 5G network, LTE network, Ethernet network. So the question about where is identity managed, right? You can't use a carrier or any individual network element to manage enterprise identity. That just doesn't work. And so all of the cryptographic work that goes on in your, in 5G with regards to managing keys, et cetera, that's all not useful if somebody in a carrier store is going to swap out a SIM and enable the takeover of someone's identity on their mobile device, which has happened multiple times. I think that happened to Jack Dorsey on Twitter. That's how his Twitter feed was compromised. So the whole point is cellular networks, enterprise networks, Ethernet, you don't trust any of that. The identity's got to be managed at the IT system, and you can't outsource that. It's got to be owned by the enterprise. Who owns identity is absolutely vital. And I would also say, in general, right, we have to be thinking about cellular networks, 5G and the rest are only part of the enterprise network. If you're using features or identity for any one network component as your key, how does that map into an Ethernet? How does it map into the LAN in your business? How does that work for your laptop that's plugged or your desktop that's plugged in? So again, it's just we want networks that are secure. We want them not to be able to be taken over for downtime, but you can't entrust your security to anyone except where the information is stored and managed, and that's not going to be a carrier. It's not going to be some provider. It's got to be the enterprise itself.
All right, thanks very much, Milo. Tim, any thoughts on that?
I'd agree with Milo that standards don't need to really be changed. And just to build on that, I think that the move towards zero trust architecture would also can be concurrent with broader adoption of the Open RAN that we've heard some of the panelists earlier in the week talk about, which will provide more options and flexibility for private and commercial deployments and hybrid models of both. Thanks.
Thanks very much, Tim. So we have another question, and this one is, do the same Verizon security and policy practices also apply to Internet of Things devices hosted on Verizon's network? Senorita, it's obviously a question for you.
They should.
All right, thank you. So we have another question. First of all, the attendee is thanking us all for the great presentation. So thank all of the panelists for the great presentation. Any ideas on using blockchain technology to enhance zero trust? Good question. Tim, any thoughts on blockchain?
That is an area that our EPRI cybersecurity team have looked into. We've done some white papers and thought leadership reports on it. We have not found a application or integration into telecom yet. Not saying that that's not possible. It could be an enabler for some zero trust or other mechanisms that are still emerging.
Thanks, Tim. Wayne?
Yeah, so I guess in general, I'm not a huge fan of blockchain. I would feel like it's a solution looking for a problem. The one place where I've seen it, or I feel that it probably is best useful, is in this concept of smart contracts that it's being used for. I have seen blockchain being talked about when you go to much more like distributed software-defined networking approach, where you don't have all the control in one place and you want to kind of distribute that out through the network. So there may be something there. I haven't looked at it in detail. I actually don't know how that really meshes with what we're calling zero trust here. But there may be something there when you're going to not purely centralize and you're trying to distribute things and control throughout the network. That might be a place where you would do something like that.
Thanks, Wayne. Milo?
Sure. Blockchain is a distributed ledger. And so I tend not to use the term blockchain because I like more boring things that make it not appear to be magic. And so any place a distributed ledger could be substituted by a database, that could work too. Blockchain has some advantages in terms of trying to decentralize administration. It's not clear that is useful in all cases, particularly in the question is really about how does that help you manage identity. So transaction logs and identity management seem to be different animals. You might use blockchain technology as part of a scheme to sort of distribute cryptographic identities, credentials, et cetera. But I think there are better solutions in general for that.
Thanks, Milo. Senorita?
I don't have anything to add. I think I kind of echo Wayne and Milo's points there. It is being explored for smart contracts, right? And so on, but it's more transactions than anything else. So Maybe there are points in different parts of the network that may be useful, but I'm not 100% sure across the board that there's an opportunity there.
Thank you. So we have a question for Wayne. Your point on cybersecurity aware adaptive NFV, likely as many organic implementations. Question, how would you envision an industry standard to support this functionality, given the nature of security by obscurity?
So I guess I would work really hard to do away with security by obscurity, because that's just a really bad policy. I mean, I used to joke when we were looking at tactical networks, the best thing we could do is just give our adversaries the specs to the networks, because they're incomprehensible, and they have a much better job trying to reverse engineer things than trying to figure it out from the specs. But I actually think, from what I've seen of, and particularly the security paper that Sangeeta put the link to in her slides, I think is a really great way. It does a nice, thorough job of describing the security architecture of 5G, and it certainly removes, I think, a lot of the obscurity there. And so I think, you just got to be clear about what these protocols are. And I think there's probably a pretty straightforward way to define standards for how different virtualized network functions can communicate if they're going to try and develop this network situational awareness inside the network.
All right, thanks, Wayne. So, I do have a follow-up to that, something I've kind of been wondering about. So we put out all of these standards. That also makes it easier to figure out how to attack these networks as well. While I understand what you're saying with removing the obscurity in this, do we incur risk by doing that, do you think?
So there's like another Kirchhoff's law or something like that with cybersecurity, that you want to make the really important parts of the security something that you can change, right? Like a key. You don't want to have your jewels be something that's hard coded into your system. And so I think particularly things like Milo has been talking about with zero trust, is that you need to build the system assuming that there's something bad in there, and somebody can get a hold of the specs even if you're trying to keep it secret. So you probably do. I mean, if indeed you could really keep all these secrets secret, then you are losing something by exposing them in standards. But given that at least the determined adversaries are going to be able to get a hold of your specs, even though you're trying to keep them secret, I don't think you lose quite as much.
All right, thanks, Wayne. Let's move on to the next question. And I'm not sure, I guess we'll open this up to anybody who'd like to answer it, but can DSS enable Cbrs to work without a centralized SAS system? If it can, how would the incentive and policy, or what would the incentive and policy look like? And I'll ask, does anybody want to tackle that one? Milo?
Muted.
Yeah, I'm not hearing you, Milo.
How's that?
That's much better.
I assume by DSS, the person's talking about sensing. The issue with SAS is you have to have an ESC network to sense the Spin 43 radars and other users. That ESC network is critical for understanding when a primary user is active, and you have to move users around to not interfere with that radar. You could imagine a world where that's being done not in a centralized way, but it's pretty difficult, because I don't think you can get the equivalent performance from a user terminal sensing the radar as you do from these ESCs that are out there. And more generally, there are certainly cases for satellite and other kinds of systems where a user may not be able to sense the signal that they're going to interfere with. And so there needs to be some form of intermediary. That could be done in a distributed way or a centralized way, but it's not going to be done by the end node itself.
Thanks, Milo. Appreciate that. Next question. And again, I'll kind of leave it to the group for who'd like to tackle it. How many different types of policies are there for user equipment access? Any volunteers? Oh, Tim?
No immediate thoughts on that. I don't know if
Okay.
Go ahead.
Yeah, I could try and take a shot at it.
All right, cool.
So if you think about what does that mean, user access policy, it means sort of what device, who's the user identity, and what their role is. And so you don't want to think about this in a mode of thinking, guest access, everybody can access read-only, or only a certain user group can actually sort of write. What you want is to actually think about your information not in terms of what your Active Directory login is, or what your OAuth credentials are. What you want to think about it is who in the org needs what rights. And if you think about that, and then you could see that it's really huge, right? It's not about just a few policies. It's really thinking about who do you want to have access to that piece of information. And so it's not about, again, a particular user group or domain admins or et cetera. It's really thinking about your enterprise, what's the structure of it, what the workflow is like. This issue about thinking about role is very critical in getting real value out of zero trust networking. And that's the area where it's difficult for a lot of organizations to deal with, who have just been thinking about Active Directory and this user has access or this group has access. Role is much more sophisticated than that.
Thanks, Milo. And we have another question for you that just came in. So you stated who owns identity is vital, and we need to focus on where the info is stored and managed. Could you speak more to that and how this works with edge computing?
Sure. So if you think about a cloud-centric world, if your org is accessing data in the cloud, you're going to use AWS's or Google's or Microsoft's credentials, right, to gain access to that. Edge compute is simply a piece of a cloud instance that's forward deployed, closer to the user. Its identity and access control ideally should be stubbed off of whatever you're doing, whether that's local to the organization and sort of arbitrated by some cloud entity, or you're a cloud native and all your identity and management is sitting in whatever cloud resources you're using to enumerate your users, what roles and what permissions they have. A good way to think about it is, who do you trust to control your badge access? Right. So who's authorizing employees to be able to get into buildings, right? That's the kind of, when you think about identity and access control, it's really got that physical analog. Like who's determining who gets in and out of your facilities, who gets in and out of your information. And so wherever that information is stored, that's going to be where the identity management is going to have to be owned. And that's why I say I think enterprises have to own that themselves. You can't, because who knows what role it is? Who knows what Tim's role is at EPRI that says what information he has access to. At Google, I can't get at our finance systems information. I'm not authorized. I'm not in the finance org. Who knows about what your role is? It's very hard to do that if it's some external party. That can be instantiated in a cloud framework, but the enterprise has to own it.
Thanks, Milo. Senyogeeta, do you have any thoughts on that?
No, I'm good.
Okay, thank you. So we have a really interesting question here that I think everybody should take a shot at. Where should the industry focus on when trying to isolate information and compute to authorized activities? How can information leakage, e.g. through multi-tenancy in hardware and especially through side channels, be tackled? So if we want to just take that one at a time, maybe Tim?
Yeah, that's obviously a very broad and complex problem in terms of in the utility world. We're dealing with the need for centralized information and cloud-based systems as well as edge computing, and bringing all those things together and ensuring that they can work with comprehensive security. It's a great application for zero trust type architecture. The side channels, it's another whole area of research that we're looking into in cybersecurity. So good question. I think the whole scope of it is relevant for the industry to focus on.
Well, thanks, Tim. Wayne, any thoughts on where industry should focus in this area?
Yeah, so I guess I'm interpreting this maybe a little narrowly, but talking about slices and inter-slice security, right? And can I figure out, what's going on inside one slice, even if, I'm not inside that set of resources that have been set aside for that slice, the logical resources, but if I'm like riding on the same hardware, or can I do something that kind of influences what goes on in a slice by stealing resources or something like that? The only idea I have for this is sort of that idea I was talking about earlier about running something on that hardware that's trying to figure out, understand, is information leaking? And doing that kind of real time as you're running the network, have like a monitor sitting there to understand, can I figure out what's going on in the slice, or am I getting the performance I want? Is somebody else doing something that's stealing resources away from a different slice in there? That's just where mine goes in that particular problem.
Thanks, Wayne. Milo?
Sure. I think this is one of the most vexing challenges that every cloud provider has to deal with. That is to say, think about what is Intel's latest vulnerability that's been seen, or some breach in a trust zone and an AMD processor, in an ARM processor, et cetera. And that's not just for cloud, but it's also for mobile devices too. If you just think about what information is present on the edge device, I think this is an area where organizations this is one of the reasons why I think people have really been moving to cloud compute, because you've got the sort of best people in the field working on trying to isolate the compute stack from vulnerabilities in the hardware below it. And that's an area where Google has put enormous amounts of resources. And, our team that finds holes, spectrum attacks and others is focused on that. I think that's, it's one of these things that you have to be updating constantly, thinking about how to segment information and how to use cryptography. I think if data is encrypted at rest and encrypted in flight, not just in flight, but also at rest, that can be helpful in dealing with these kind of challenges as well. And certainly if you're going to run your own compute, you need to be thinking about how data is encrypted at rest.
Thanks, Milo. Sanugita, any thoughts or things to add?
Yeah. That's a great question, and I wish there was a simple answer that we can say, let's focus on this, right? I think my panelists have identified a few areas that may be meaningful, but I think we can't rest. I think we have to look at all aspects. I mean, there's a constant evaluation, and like I enumerated, we have multiple layers, and it's not just physical, right? Yes, you have a mobile edge compute perhaps, and you have a cloud compute at the edge, and so on. That comes with physical security as well as cyber security. I guess tools and technologies that we'll need to continuously evaluate, and it's the hardware and there's the software. So vulnerability in hardware, how do we address that with some of the cloud things that Milo just mentioned? Redundancy and resiliency is important as well. I mean, resiliency comes in various forms. The need for resiliency, even the weather is every year for us a problem that we need to address, right? So I think we have to look at it as a multi-pronged solution with multiple approaches to tackle different things. So I don't know that there is a magic bullet that we can focus on and have all the problems resolved.
Thank you. Great answer. So I think I don't see any new questions coming in, but I think we have time for one more. Unless Tim, you had something you want to add to?
Yeah, just to finish up on that last question, one kind of a contrarian thought is that at least in critical industries, one approach toward mitigating the type of questions of information leakage, multi-tenancy, and such is just for those extremely critical applications to avoid using those approaches, avoid virtualization, multi-tenancy, and all those things. And certainly that's not a long-term approach, but in some cases the industry can take a slower adoption to avoid those unknown threats that may exist in those areas.
Thanks, Tim. So yeah, I do think we could squeeze in one more question here. And I guess this is one that we kind of talked about before, but for your particular industries, what's the most critical threat you see? And so, Tim, maybe we'll start with you. What's the biggest threat you see for your industry?
Well, yeah, the electric industry has certainly cybersecurity overall, and preventing attacks and outages caused by bad actors, individual or national, has been a huge area. And this, I'm in telecommunications. We work closely with cybersecurity, but we have a team of cybersecurity experts that are deeply involved with the industry and the government and have various levels of security clearance. I can't get into what all is going on and the details, but I know there's a lot of activity, a lot of work, a lot of effort to ensure that the grid and its control systems are secure and resilient to those types of attacks.
Thanks, Tim. Sanugita, what's the biggest threat Verizon sees?
Oh boy, I don't know. There are. I don't know that I have an answer for that. I think it may be. I mean, security is definitely an issue that we are, constantly on the top of our mind. Security for the customers and security for our people as well. Resiliency, I think, is another thing. The weather is like I said, a constant thing that comes, and you might think it's a dropped call, not important, but clearly when you're battling fires and thunderstorms and hurricanes and so on, so that becomes an important call that for a first responder, for a service provider, and so on. So threat can mean different things, and if you look at it from a different context, but if you look at it narrowly, these are some things that we are constantly on top of our mind.
Thank you, Sanugita. Milo?
That's an interesting question. My sort of first reaction would be to say, nation state actors, because the same sort of adversaries that the U.S. government has are sort of the same that we have in terms of trying to penetrate into our systems and gain access to information for our users, and we take that very seriously. But I would say maybe the biggest threat is actually complexity management. That is to say, if you think about all of the different layers, all of the different systems, the multitude of access mechanisms, right? How do you keep all those things managed well? And that's really the heart of resiliency. I think trying to actually think about identity management, cryptography in a place where you can have simplicity and not have infinite number of choices there is going to be important, particularly as 5G's attack surface is so much bigger than what you see in LTE and in wireless networks in general. How do we think about those things and managing the complexity so that the configurations don't lead you into dangerous zones?
Thanks, Milo. Yeah, good answer. Wayne, any last thoughts on this particular question before we move on to our individual meetings?
Yeah, I was going to go with the complexity thing until Milo took it. I was going to add to that, it's not even just necessarily, attacks, right? It's just, the more complex these things are, the more corner cases there are that you just can't possibly explore. So some system could get in some bad state due to some sort of random event. And when it's so complex, you don't necessarily foresee that or know how to get out of it. But what you started with, Milo, prompted me to a different idea, and that's just privacy in general, right? I think a lot of these systems, there's going to be a lot more data out there. We're going to be having a lot more wireless systems on us. And it's just going to be an opportunity to create more of a footprint of where we've been and, what our behaviors are. And how that might get actually aggregated, and losing privacy without really knowing about it, I think is another thing that I'm concerned about looking at.
Thanks, Wayne. I think, if I'm not mistaken, and maybe Keith can jump in, but I think we're about out of time.
Yep, we're out of time, just barely beyond schedule. So it's time now to go to the breakout rooms for one-on-one interaction with the panelists and our technical speaker. So information on accessing the breakout rooms is in the ISART app, or you can use the links in the confirmation email you each received. So don't forget to close out of this window and then go into the breakout room. Thank you.
Thank you.
Thanks very much, everybody.
Thank
We'll
you.
see you back here at 1. Thanks to all and the panelists.